Good morning. Wonder if we've got anybody on here. Nope, nobody's on. Well, we'll just be patient. It's just 9:20, and the students come on at 9:30. Well, Earth calling students come in students. Well, what are we going to study today? Let's see. I think the topic is stress. The topic today is stress. Normal stress, shear stress. Pending stress, bearing stress. That's the topic. Does that show up on? Oh, look, I've got a student. Nicholas is with me. Yay.
I'm with you, Mr. Griffin.
Hey, that's what I like to hear. Nicholas is with me. Wonder if we got anybody else. Let's see. Not yet. You're my one and only right now.
Well, I'm sorry about that. I'd hate to be stuck with me too.
They'll show up.
Yeah.
We'll just be patient. Do you have any questions while we're waiting for the others?
Well, not really. I haven't looked yet, but did you manage to post a video for the dynamics class yesterday?
The question is, did my IT person post the? I think she did.
Yeah. Okay.
I think she did. She's pretty efficient.
Well, you could probably trust her, being she's your daughter and all, right?
Yeah. Yeah, she knows what she's doing.
Yeah.
She's 30. How old are you, Nicholas?
39.
Oh yeah, we've talked. You're in my physics class, aren't you?
Yes, sir.
Yeah. Well, we'll meet again on Thursday.
Yeah.
I posted the lab for Thursday. Did you pull it up yet?
Oh, not yet. No.
I'm pretty sure I put it's on content in the physics class.
Okay.
So you can pull it up and read it. That'll be fun for Thursday night. Hey, we got another customer, Ben. Unmute and say hi, Ben.
How's it going?
Yeah. Doing okay. I
Good.
stepped outside to feed the dog, and it's a beautiful day out there.
Yeah, it is nice out.
Well, we got 5 minutes left. Oh, there's another wonderful student. Look at there. There's Chase and Mohammed. Yeah, we're getting a good class. We got 5 minutes. Feel free to ask me anything if you have a question. We're going to talk about stress. That's the big topic in this class, you know, stress.
Hi, Mr. Griffin.
Hey, good morning. I
Good
heard,
morning.
is that my friend Ashley?
No, this is Mohammed.
Who was that?
Mohammed, this is
That was
Mohammed.
Mohammed. Hi, Mohammed.
Hi.
Yeah. Let's see who else we got here.
So, can you go over the homework problem 1-11?
Yeah, now Mohammed wants to talk about 1-11, right, Mohammed?
Sorry, 1-14, not 11, 1-14.
Let me find it, just a minute. What page is it?
It's, hold on. Page number 55.
Thank you so very much.
You're welcome.
Yeah. Now it's part of your homework, but I don't mind. We can talk about homework. It won't
Yeah.
hurt us any. I can do the whole thing, or I can just answer part of it. What seemed to be your problem with F-114?
I was actually confused about the statement when it says if it is subjected to double the shear. That was the
Okay,
problem.
well,
I didn't
Let me
understand
show you that, Mohammed. Yeah, there's a connection here at A. There's the artist rendition of it. And see, it's got two brackets. Is that showing up on the, yeah, it's got two brackets, and then the pin goes through those like that. Kind of hard for me to draw that, but I'll try. See, there's a pin through there, and then there's this member. There's another member that's coming out this way. That's what AC. AC is out here. And kind of hard for me to draw there, but I'm trying. Do you see how they have two brackets? And so when you go to get the shear, trying to remember what the force was there. Let me see if I can remember. I think you have I think you have 800 pounds and 600 pounds. At A. And we can go through that if you want. But see, if you have 800, 600, and you take the square root and you do all that, you will get 1,000. So to get the shear stress at A, you take 1,000 pounds, and you have to divide it by the area. But see, you have two areas because there's two brackets. You have two areas, and so you go 2 times pi 0.25 inches squared over 4. See, you have two of them because you have two brackets. And when you do that, you'll get your shear stress. Let me do that. Well, I got an answer. I wonder if it's right. I'm getting 10186 pounds. Let's look in the answer book and see what the answer is to F114. They said the shear stress at A is 10.2 K. This is wrong. This is pounds per square inch. They said that it's 10.2 KSI. Well, that's what that is. Hey, we got the answer in the back of the book. How about that? I skipped a bunch of stuff there, Mohammed. Are you happy with that now? Do you understand it now?
Yes, it was just confusing how, because in the diagram it wasn't showing that at 8 has like two
Yeah,
pins.
it's
It
got
was
two.
just showing this one pin. That's why I was
Yeah.
confused why they're dividing by 2.
Yeah. You okay now?
Yeah, I'm okay now.
Anybody else? I mean, I can go through it more if you want. Just speak up, anybody that needs help. I've got a wonderful class here. Let's see who we got here. Oh, big class. Muhammad, Alex, Nicholas, Ashley.
No, why we have to take, why we did the magnitude of 800 square plus 600 square? Why we did that?
Why did we do that?
Yes.
Do what, Mohammed? Why did we do what?
Why we take the square root of 800 and 600?
Oh, okay. Well, I'll be glad to show you that. And we got, look at all these wonderful students. Noah, Julian, Jackson, Darren, Chase. Let's show you that. Right now, I'm helping you with your homework there. However, just a minute, when's that homework due? Let's see. F114. Oh, that was due last night at midnight. So that's okay. We'll go over it. But it was due last night at midnight, I believe. But see, what you have to do is you have to find the external forces first. So here's this. Oh, gee, did I forget my protractor? Doggone it. Well, I can use this ruler here. Now, you know, when you do your work, you're supposed to have some kind of engineering paper. Now, I don't think you can see, but this has got a grid on it. It's real cheap graph paper. It doesn't show up on there, sorry. But I bought a pad of this for 88 cents at Walmart. Or you can buy that expensive engineering paper if you like. But first you have to find the external forces. Now the external, if this is 4 feet, let me draw that. Okay, 4 feet. Well, we use inches, I guess. Okay, there's 4 inches, and then there's 3 inches down here. That puts me to right there. And here's your other piece right here. Okay. See, this is 3 feet. This is 4 feet. And of course, that's 5 feet. That's your 3, 4, 5 triangle. And here's your double brackets. Remember I was telling you about those?
Yes.
Those double brackets there. There's a single bracket here. There you go. And then there's another member right here. Let's label all this stuff A, B, C, D, and E. Okay, I did it to scale. Do you do your work to scale? Well, you're supposed to. Now let's find all the external forces. See, first you find the external forces, or external loads, you could call them. And then from there, we'll go to the internal loads. But first you have to find, first have to find the external loads. Now I like to put my forces in red, so I've got a red marker here, and they said this is 600. Okay. £600. Does that show up red? Kind of. Now, wait a minute. I goofed up on this. This is not a bracket. This is a rocker. It's a rocker. And it can only give you a normal force. It can't give you an up and down force. It can only give you a normal force. So I'm going to draw the normal force in red. And then the other force has to go here. Do you remember me telling you, you draw your free body diagram
Yes.
and you look for 0, 2, and 3 force members. Well, this structure is a 3 force structure. 3 force structures or 3 force members are either concurrent or they're parallel. Maybe I should write that down again for you guys. 3 force structures are either concurrent or else they're parallel. Now let me ask one of my excellent students here. Let me pick on Shane. Unmute, Shane, and I want you to tell me something. I want you to tell me what this word means, concurrent. Do you know what it means, Shane? And if you don't, it's not the end of the world. What does
No,
it?
I'm not sure.
That's okay. We'll pick on Noah. Unmute. Do you know what that word concurrent means? Unmute Noah. Earth calling Noah.
Does it mean they're all through a point?
Yes, good going, Noah. Proud of you. Now, do you see how these forces here, these two forces here, go through that point right there? That's the concurrent point. That is the concurrent point. If you have a 3-force structure, all the points have to go, all the forces have to go through the concurrent force point. Well, that means that the force at A has to go through the concurrent point. And so A is doing this. There's your force at A. Now we're going to find out what those forces are. Now the way you solve for forces is you take the moments. Take the moments about A, and you have a negative 600 pounds times 4 feet, and a positive B times 3 feet equals 0. And you solve that, and you'll discover that B has to be 800 pounds. Now what that means is the component of A has got to be 800 pounds going to the left. If this is 800 pounds going to the right, this has got to be 800 pounds going to the left. Now you see that 600 pounds going down? That means A has a component of 600 pounds going up. Now Mohammed asked me how I knew that A was 1,000 pounds. And I wrote it out for him. I went the square root of 600 squared plus 800 squared is 1,000 pounds. He wondered, well, how did I get the 1,000 pounds? Well, that's how. These are the components at A. So that means that A is 1,000 pounds. And so when you go to find the shear stress at A, it's 1,000 pounds divided by 2, because there's 2 brackets, pi 0.25 squared over 4. And you will get the answer. We had it on the board. I erased it. Now let me do it again. 1,000 pounds divided by okay, I got an answer. I got 10.2 KSI. And that's what the answer book says. Mohammed, do you understand now
Yes,
that
I got
problem?
it, sir. Thank you so much. Yes, thank you.
Anybody else? Anybody else? So you're all happy? The topic today is stress. See, we found the stress. It's 10.2 KSI. But what does KSI mean? Let me ask one of my excellent students here. How about my friend Samuel? Samuel, unmute and tell me what the heck is a KSI, Samuel? What's a KSI?
Is it kilopounds per square inch?
That's it. He's got it. It's 1,000 pounds per square inch. Good going. Excellent. Anything else from anybody before we have more fun? No, notice there's a method in this stuff. You make a free body diagram to scale. Hey, I measured that stuff. I got me a ruler. Look, I got a ruler and I measured stuff. That thing is done to scale. And then what? Then we found the external forces in this case. And I put them in red. Put your forces in red. Then I looked for three force members. Well, the whole thing is a three force member, so it's concurrent. That helped me, see? That helped me a lot. Now I was able to figure this force at A is 1,000 pounds. It has components. And then you can go for internal loads. Now what they wanted was they wanted the force on the pin. Well, there's 1,000 pounds on the pin. That's an internal. And so you can get this shear stress on the pin. You know the formula. You know how to do shear stress. It's V over A. That's internal. It's an internal, shear is an internal force, and shear stress is force divided by area. Okay, well, if you're happy with all that, we'll do something else. Here's your chance. Go ahead and ask me something. Anybody? Otherwise, we're just going to keep doing stresses here. Okay. Well, let's do this one. Make some room here. But that's the plan. Which one do I want to do the most here? Let me think. You've heard of normal stress and shear stress, but I don't think I've told you about bearing stress. Well, let's talk about bearing stress. That won't hurt us any. Look at problem 171. Let me see if I can find that. 171. Hey, there it is. I found it. We're going to look at problem 171, and it's got bearing stress. It also has normal stress. But they've got a pin there. It's a bolt. No, it's a bolt. And it's got a nut and two washers. Okay. Bearing stress is 2 KSI. Tensile stress is 18 KSI. That's the maximum. We want the tension in the bolt. Okay. We want the maximum allowable tension in the bolt. Well, all right. Let me draw this bolt. Now there's a bolt. Artist's rendition of the bolt here. Of course, there's going to be threads on the bolt, and then there's a nut. There's a nut. Of course, those would be dashed lines there inside, wouldn't they? That kind of gives you a feel for it. That would all be hidden away there. Let's look at the forces on that bolt. Oh, wait a minute, I forgot the washer. There's a washer here and another one here, right? Yeah. There's a couple of washers here. Okay. Now I get the feeling like maybe maybe we're tightening this up. See, there's a screw here, and there's a nut. Here's the nut, and we're tightening that nut up, tighter and tighter. And you know what that does? That stretches the bolt because you've got these boards here. You got this board here, and you got this board here. And you're tightening this nut, and it stretches the bolt. In fact, the bolt comes down a little bit. It comes poking down through here a little bit as you tighten it, as you screw that nut, and it puts a lot of tension on the bolt. Okay, that's normal stress. The normal stress on the bolt is going to be the normal force on the bolt times the area of the bolt. Now let me read this. And they said that the allowable tensile stress is 18 KSI. Well, that's this here. That's their maximum that they're going to allow is 18 KSI. And what are we supposed to find? Determine the maximum allowed tension in the bolt. Well, that's what this is. This normal force is tension. That's tension. It's a force. In this case, pounds. So we're going to find it. Now the area of the bolt is pi over 4. Now what's the diameter of this bolt? 0.31 inches. So we have us an equation here, and we can find the tension in the bolt. They don't want us to tighten it any more than that. And they want to find what that maximum tension is. Well, you got calculators. You can do this as well as I can. Go ahead and do that. I'll call on one of you. I'm going to do it. I'm going to find this tension. You can put T there instead if it makes you happy. But it's tension. Here goes. You do it. Well, I found the maximum allowable tension in the bolt on my calculator. And let me ask my friend, Noah, unmute. Have you got that yet, Noah? Have you plugged this in and gotten the maximum normal force there? It's tension, Noah.
See, what's that number in the parentheses you got there again?
It's 0.31. This is problem 171. It's on page 58.
Yeah, I got 0.0754.
Well, that's not what I got.
Let's see.
We're trying to solve for this n here, Noah. What you do is you take 18,000 and then you multiply by this stuff here.
Oh, yeah.
Go ahead and do that. And tell me what you got.
I got, let's see, 1,358.
That's what I got. Now those are in pounds, Noah. Now, if they wanted it in kips, Noah, do you know what a kip is?
Yeah, isn't that 1,000 pounds?
It's 1,000 pounds. So there's the answer if the tension in the bolt is the problem. But we also have to look at the bearing stress. See, this is normal stress here. And in fact, it's tensile stress. We just looked at the tensile stress, and we found that if you have this 1.358 kips, you've just maxed out the tensile stress, and you might have a problem with the bolt. But we also have to calculate the bearing stress. So let's do that. Now you see this washer here? As you tighten that bolt and start squeezing these boards, they look like they're made of wood. Is it wood? Board. It says board, so they're made out of wood. What happens is, if you tighten it too much, you'll start kind of making an impression in the wood. Here, I'll try to draw you what I'm talking about here. I need some room here. See, here's this board. Our artist's rendition of this board here. And as you tighten that bolt, that washer, there's a washer, will push itself into the board and kind of, I don't know if I can do this. It'll make a kind of indentation in the board. It'll just push itself. It's kind of hard. Our artist view there, we tried to draw the it's pushing in that board, and if boards are pretty soft, it might just make a impression in the board there. And they call that bearing stress. Bearing stress is when you have an area, you have a normal force acting over an area, and on that board, it can make a impression that looks like a washer shape on the top of that board. Of course, there would be one here. There's a washer down the bottom. There would be an impression on the bottom board. I think you understand that, I hope. And here's the formula for bearing stress. It goes like this. This is your bearing stress. I'll just call it bear. There you go. That will be the normal force divided by the area of your washer. Now, the area of the washer is pi over 4 0.75 squared minus 0.5 squared. They said the diameter, the outside diameter is 0.75, inside diameter is 0.5, and they told us the maximum bearing stress. It's 2 KSI. Okay, it's 2 KSI. So now we have this lovely equation here, and we're going to solve for the maximum force in the bolt that you can allow so you don't wreck the boards. You don't want to have a washer-shaped hole there in the boards. So get your calculators out and do that, and let's see what you get. I'm going to try it. And I'll call on one of you. Get your calculators, solve for the normal force. And we'll get the maximum force that you can have in your bolt. And I got an answer. Now let me go to one of my wonderful students here. Julian, unmute, and have you got that yet, Julian?
I got 490.87.
That's what I got. We'll just round it off. So if you get 490 pounds of tension in that bolt, you're on the verge of having a problem with bearing stress. Now, of these two, the 1,358 pounds or the 490.9 pounds, which is the correct answer? Well, this is the correct answer because as you tighten that bolt, you'll get to a tension in the bolt of 490 pounds long before you have 1,358 pounds. So the problem in this case is with the bearing stress. It's not that the bolt doesn't have a problem. It can handle a lot more tension, but that soft wood is going to be wrecked by the bearing stress, and this should be the answer. Okay, let's look it up. 171. Go to the back, and we'll see how we did. 171. Here's what the answer book says. 171. They use P. I don't know why, but some books use P as just a dummy variable for a normal force, and they got 0.491 kips. Well, that's the same thing as what we got. We got 490.9 pounds, and the book says 0.491 kips. Yay, we did great. We did that. So now we've talked about bearing stress.
Mr. Griffin, do you know why we subtract 0.75 from the point minus 0.5?
Oh, thank you for asking. See, we're trying to find the area of a washer. Now, if you just had a circle, the area would be pi over 4 times 0.75 inches squared. But we have a hole in it. There's a hole in this circle. It's called a washer. So what you have to do is the area of that washer is pi over 4.5. Actually, it's a little bigger than that. It's more like, it's a funny looking washer. Pi over 4.5 inches squared. You have to subtract the area of the hole. Do you understand?
Yeah. Okay.
So you have to subtract the hole. This is the area of the hole. This is the area of the outside circle. The hole isn't there. Oh, the wire, this is made of metal. It's called a washer. Do you understand, Mohammed?
Yes.
I'm waiting for that yes.
Yes, I'm saying yes.
Yeah, is that yes a real meaningful?
Yes.
You got it.
Yeah, I got it. Yes,
All
I got
right.
it.
All right, good. Okay, well, let's do something else. That was fun, unless there's a question. Okay, we'll do something else. Let's do this one here. I'm going to erase all this if you guys are happy. Here's your last chance now to speak up. Okay, in other words, you understand that. That's good. So we've studied, we're studying stress. I've told you before that this whole course is about stress. It's stress. Okay, now this problem here is 154. Before I do 154, let me go back and show you some basics here. Let's suppose you had a rod under tension. Got a rod under tension. Let's call this area here A sub 0. It's a perpendicular cross-sectional area. And let's section this. We're going to section it like this, maybe, yeah, like that. And there, this would be internal. We'll put a dash line there. See these dash lines? We want to find the normal force and the shear force, I'm sorry, the normal stress and the shear stress on an inclined area. Okay. Now I picked a angle here of 30 degrees to make this fairly easy for us. See, I picked an angle of 30 degrees. And let's just pick this angle. Let's just say this force is P. The book likes to use P for normal forces. The normal stress is going to be, well, we know what it is. It's the normal force over area. And the shear stress is the shear force over area. We know that. But if it's at an inclined plane like that, how do you find the normal force? Well, see, the normal force is going perpendicular to that area like this. See that normal force? And the shear force is going parallel to the area like that. Let me draw those forces separately. Let's suppose this is P right here. So you can break this down into components. This is called the normal component. And this is called the shear component. And those two will have to add up to P. I tell you what the normal component is. It's P cosine, in this case, of 30. See that angle 30? That's that same angle 30 there. Can you see that? And this one here is P sine of 30. So we made some progress. We know that this is going to be P cosine of 30 divided by the area, and this is going to be P sine of 30 divided by the area. But see, this area here is bigger than the cross-sectional area. This area here is equal to the cross-sectional area divided by the cosine of 30 in this case. You could show that with trig. And so when you solve this, you get the normal stress is P cosine square root of 30 over a sub 0. And tau is going to be P sine 30 cosine 30 over a sub 0. I skipped a step there. But I'm going to give you the equations for a slanted area internal to a member under tension. And in fact, this is the equation where theta is just a dummy variable. So let me write that for you. And then we'll work a problem. But I needed to go back through that with you. The normal force on this slanted area is equal to the external force cosine squared of theta, where theta is this angle here. See it? Divided by a sub 0. The shear stress is P sine theta cosine theta over A0. Why don't you write these equations down in your notebook, someplace where you can get to them, and we'll practice them. We'll solve a problem. I thought we'd solve problem 154 first, and then we can solve some others. Did I lose everybody? Give me some feedback. Are you okay with that?
Yeah, it looks pretty good.
Okay, well here let's do this 154 or maybe another one so that we can feel confident about this. We got our equations now. Write these down. Write those equations down. Now this angle theta is with, if you take a perpendicular cross section, it's the angle with whatever internal surface area that you want. You've got to know that there's shear stress and normal stress inside a piece like that. Even if you just had a circular cross section and you put it under tension, get yourself just a steel bar, circular cross section, and pull on it on both ends. You have normal force inside, obviously. Obviously, you have normal force inside, but did you know there's also a shear force inside? And there's normal stress and shear stress inside. It turns out the maximum shear stress is at an angle of 45 degrees. The reason for that is your equation goes like this. If this angle is 45 degrees, you will get your maximum shear stress. let's just figure it for some different angles. Suppose here, let's have the angle, and we'll calculate the shear stress, just for fun. If the angle is 0, you all know what that would look like. That's where you just cut it straight. There is no slant. And the sign of 0 is what? Does anybody know what the sign of 0 is? What's the sign of 0?
0.
Somebody said something.
I think
I
it's
think-
0.
Yeah, it's 0. Good going. So if theta is 0, there is no shear stress. But here, let's try some other angles, like maybe say 20 degrees. I want you. Hey, let's give some actual figures here. Say this is 1 kip, and say this is a 1 inch diameter. You have a 1 inch diameter rod, you have 1 kip, and at 20 degrees, now 20 degrees would be kind of like this. See that angle there at 20 degrees? It's a pretty small angle. Hope you can read my writing there. Not very clear. 20 degrees. We're going to figure out the shear stress. If you had a 1 inch diameter rod, 1 inch diameter rod with 1 kilopounds of tension in the rod, and we're going to figure out the shear stress. Okay, well, here goes. The shear stress would equal 1 kip divided by this. Now, this is the cross-sectional, perpendicular cross-sectional area. That's pi 1 inch squared over 4. And this is sine of 20 cosine of 20. All right, do it. Let's see what we get. All right, I'm plugging this in now to see what I get. Well, I got an answer of 409. I believe it's PSI. I wonder if that's right. Did anybody else get 409?
Yeah.
Yay, there's 2 of us. Well, let's do 30 degrees. Okay, I need some room here. Now, if you're doing 30 degrees, I need some room. Then the shear stress is 1 kilopound divided by the perpendicular cross-sectional area, which is pi 1 inch squared over 4. If you can read my writing, that's 1 squared over 4 times, if you're doing 30 degrees, you go sine of 30, cosine of 30. That's it. Plug it in. Let's see what happens. Well, I got an answer. I got 551 PSI. Did anybody get 551 PSI?
Yeah.
Yeah, there's somebody. Now let's do 45 degrees. Now to do 45 degrees, you know what? This A0 stays the same. The 1 kip stays the same. The only thing that changes is this angle here. You guys work that out. I want to find something that I'm going to show you in the book. We'll get back to this problem here in a minute. I want to do that problem, but I'm trying to help you understand this first. I wanted to show you something in the book, but I can't find it. Let me keep looking. I haven't quite given up yet. Dang, I can't seem to find what I want. But I haven't given up yet. Yeah, I found what I wanted. Let me put up what I think that is. That's 1,000 pounds divided by pi times 4 times sine of 45 times cosine of 45. Did you get 636.6 psi? And I'm listening
Yes.
for, heard a yes. How about another yes?
Yes.
Yeah, good. Okay, well, let's go to 20, 30, 45. We'll go to 50 degrees. We can keep on going, but this is the last one I'm going to do on this. It's going to go down is what it amounts to. But if you plug in 50, these stay the same, see? Plug in 50 and let's see what we get. Here goes. 1,000 divided by pi. And 4 times sine of 50 times cosine of 50. Did you get 626.9? I wonder if I did that right.
Yes.
Yes.
Yeah. And it goes down from there. Now, like if, here, we'll do one more. I lied to you. We'll do one more. If you go to 60, it's going to get even smaller. Here goes. I'm plugging in 60 degrees now. Okay. 60 degrees. I'm getting 551 now, PSI. Interesting. Look at here. The maximum shear stress in a rod under tension occurs at a slant of 45 degrees. Now, in your book, I don't know if you can find page 6 or 89, but on page 89, there's a picture of a steel rod that they have stretched. And here, I'll try to draw you a picture here. If you don't have a book, you don't know what I'm talking about. But it turns out that steel is weak in shear stress. Steel is weak in shear stress. Now, steel is very strong in normal stress. Oh, it's a winner. It does great. But steel has a problem with shear stress. And they took this rod and they put tension on it. And if you look at it, they broke it into two pieces. Here's this rod, and this is kind of rounded off like that. And the other piece, well, actually, it necked down, and we'll talk about that necking down. But this angle here is 45 degrees. Isn't that interesting? See that angle? And this angle here and here is at 45 degrees, either to the horizontal or the vertical. It's the same. And the steel fractured. It fractured at 45 degrees. You know why? Because it's weak in shear stress. The maximum shear stress occurs at 45 degrees. Okay, any comments or question on that? Because I want to work this problem. What did I say it was? 145? Is that what I said? I can't remember now. Anybody remember what I said?
I think it was 154.
Yeah, it's one. Thank you very much. It's one. We're going to do 154, but before I do, is there any comment or question on this formula? We're going to need this formula. I tried to show you where it came from. I'm not real sure that that formula is in your book. But if you'll write it down and have it ready in your notebook or where you can get to it, here, let me write it again for you. I don't think the book tells you that formula, but you can always do it the hard way. But on 154, what they have is a rod that's oh, I lost my page already. Help me, what page is that on? I need to know where 154 is.
It's on page 43.
Thank you. It's there, page 43. Page 43. Now this rod is 2 inches by 1.5 inches. It's 1.5 inches this way and 2 inches this way. Okay, there we have it. And they're putting 800 pounds on it. And they have what they call a fish mouth weld. They've made a fish mouth weld, and they made it at an angle. They made it, this angle is 30 degrees. And it's what they call a fish mouth weld. This angle here is 30 degrees. Kind of hard to draw, but I'm going to try. Only that should be dashed, shouldn't it? That should be dashed. Kind of hard for me to draw that, but I'm trying. Yeah, it's internal. All right. There we go. But see, the angle we want is not 30 degrees. It's going to be 60 degrees. This big angle here, you always take the angle with the perpendicular cross section, not with the axis of your rod. And to make life easy, they've got 800 pounds here. I'm going to break this into 400 pounds and 400 pounds. We got 400 pounds. Total's up to 800. And I'm just going to split this. I'm going to split this rod just right down the middle. There we go. And I'm just going to get rid of the bottom part of it. I don't need that anymore. I got 400 pounds on that top part. And so now this will be 1 inch, won't it? That's 1 inch. This is 1.5 inches. And we're doing pretty good. There's some dashed lines here. Okay. And if you want the normal stress on that internal slant, it's going to be 400 pounds divided by 1 inch times 1.5 inches. That's the area. Times the cosine of 60 squared. That's it. And the shear stress will be 400 pounds divided by 1 inch, 1.5 inches, sine of 60, cosine of 60. Okay, now we're going to get those and we're going to see what they are. Okay, can you read all that? I think you can. I'm getting too hot. Take this coat off. Okay. Now I want you to do that. I want you to find the normal stress and the shear stress on this internal slant, okay? All right, here goes. Well, I got an answer of 66.7 PSI for normal stress. And now we're going to do the shear stress. I wonder if I did that right. I'm getting 115 point, rounded off to 5 PSI for the shear stress on that slant. Of course, you know, there's another slant. They call it a fish mouth weld. But on the surface of that weld, these are the stresses. Now let's see what the answers are. Go back here and look at 154. And it says, well, by Jove, it says 66.7 PSI. And for the shear stress, the book says 115. They didn't have a 0.5, but we can live with that. So we've shown you that. Now you know that there's internal stresses inside a piece. Any comments or question on that? Okay. Well, let's just work a simpler problem. That was kind of tricky. But if there's no questions, we're going to do a simpler problem. I had never heard of a fish mouth weld. Do we have any welders out there? Welders, speak up. Let me go to my class roll here. Any of you, Shane, Samuel, Noah, Mohammed, Julian, you got any welders in the crowd? Speak up if you're a welder. Ben, Ashley, Alex, Nicholas. Nobody said anything. I don't guess we have any welders. But anyway, we did a problem there. And we found an interesting equation. And you're going to write that equation down for me. Let's do a simpler problem, shall we? But again, we're going to be finding stresses. That's where it's at. This is problem F. Problem F 112. Uh-oh, I don't know where it is. Can you help me find it? F112. Trying to find it.
Page 39.
Did you say 35?
39.
Okay, one of my excellent students says 35. No, it's not 30. Did you say 25?
39.
39. Thank you so much. Yeah, there we go. Okay, well, we've got a rod here and another rod here. Now this is a 3, 4, 5. I didn't bring my big protractor in here, but I've got this little one. I can fake it. It's about like that. Now this is C here. This is A. And this is 50 kilograms. And they said that the diameter of AB is 8 millimeter diameter. Okay. And this is a 3, 4, 5. They said this is a 3, 4, 5 triangle. I want you to memorize the 3, 4, 5 triangle. Let me go through it. It's so important because teachers use this on exams all the time. If you have a 4 and 3, you all know you get 5 because 4 squared plus 3 squared is equal to 5 squared. You all understand that. And if you solve for this angle here, it's 3687. Just look up the arctangent of 3 over 4. And you'll get 3687. And this is 5313 degrees. If you don't believe me, look up the arc tangent of 4/3. Okay? And memorize that. I don't want you to have to figure that out. I want you to know that by heart. Just like you know the 30, 60, 90 triangle by heart, don't you? The 30, 60, 90. This is 1, 2, square root of 3, 30 degrees, 60 degrees. You have that memorized, don't you? Well, don't you think it's about time for you to memorize the 3, 4, 5? Well, I think it is. Now let's work our problem. Now the way you work these problems is first you draw these to scale. Well, I actually measured that angle. I got my protractor out and I measured it. And now we're going to put red stuff on here. We're going to put our newtons. So what's 50 times 9.81? That's 490.5. We know we have 490.5 newtons. And when you do these problems, you look for 0, 2, and 3/4 members. Well, this structure is a 3/4 member. Look, there's a force here. There's a force here. They all meet in a point, don't they? They all meet at point A. It's they call it the concurrent point. And see, these are all 2/4 members. Well, that's a 2/4 member, and that's a 2/4 member. Now what we got to find out is these external forces. First, you solve for external forces, and then you solve for the internal forces. Then you get the stresses. I think they want the stresses. Let me read here. Yeah. They want the normal stress in AB. Okay. Well, how do you do that? You have to use these equations of equilibrium. You know these equations. Hopefully I'm just boring you out of your gourd, and that's good. And see, when you do this in the x direction, what you'll have is C, call this force C, cosine of 3687 minus B equals 0. See, there's two forces in the x direction. Now we're going to do the y direction. Well, that doesn't have a y direction, but this does. It's C sine of 3687 minus 490.5 newtons equals 0. Ooh, how nice. We can solve for C. See it? Okay. Well, let me solve for C. Here goes. I want you to solve for C, and I'm going to solve for C. Here it goes. Well, I got a value for C. Mine says 817.5 newtons. So we just figured out what C was. It's 817.5 newtons. And now we can solve for B because we know what C is. So plug that in with me. Now I have B. My calculator says B is 600. and 54 newtons. Okay, well, great. Now we're going to give them what they wanted. They wanted the normal stress. We don't need this because you're going to memorize that for me. We're going to get the normal stress in AB. All right. Well, it's 654 newtons divided by pi over 4, 0.008 squared. Okay, do it. Well, I got an answer. I'm getting a humongous answer. I'm getting 1301 megapascals. I wonder if that's right. Well, let's look and see. This is F112. They show you how to do it in the back. Let's look it up, F112, and we'll see what they said. F112. They said the answer is the normal stress in AB is 13 megapascals. Well, that's what we got. Yeah, that's what we got. Do you see the method? You draw your free body diagram to scale. You measure your angles. You put all of the external forces in red, and you solve for the external forces using the equations of equilibrium, and then you find the stress that they want. We did. Yay. We got it right. That's the method. Do you have any questions? Here's your chance to ask questions. Well, we've just gone over stress again. We learned something new, bearing stress. We learned about stresses internal in a tension member. It was pretty fascinating stuff. But I think that's going to have to do it for today until we meet on Wednesday at 9:30. And you got some homework there.
Mr. Griffin,
Yeah.
what page was that F1 or F12 on? F112?
Oh, thank you for asking. It was on page
39, I think.
What page?
39.
Help me.
It's on
I
page
think-
39.
Page
Okay, I think I
39. Thank
remember.
you so much.
Okay, I found it.
Good.
I remember you
Excellent.
guys saying that now. Thank you.
You are so welcome, page 39. Any other comments or questions?
The connections on the B and C, they are not pin connections. They're just.
Yeah,
Are they pin?
they're pin connections. Yes, they are.
So why we didn't do the, you know how you normally do, like draw the components, like if it is a pin connection going in the next direction in the y direction, can we do that here as well?
Well, is no y direction at B. Now at C, we have a y direction and an x direction, but there is no y direction at B. It's entirely horizontal.
Okay, got it. Thank you so much.
Did that answer your question?
Yes.
Anything else from anybody? Well, okay, enjoy your homework. Now that homework, it's on Blackboard, and let's see what it was. homework. You're supposed to do 178 and 186. And it's due the 28th. Well, when's the 28th? That's Friday. So you got, no, that's not right. No, that's right. That is right. It's not Friday. It's, yeah, it is too. Your homework is due Friday. It's on Blackboard. You guys have been doing pretty good. I need to finish grading some of your homework. You're doing good. I'm the one that needs to get busy and not be too lazy. Okay, guys. Well, that's it for today, and I will see you soon, I hope. Goodbye, y'all.
Have
We're
a
supposed
good
to
one.
say goodbye.
Goodbye.
Bye.
Bye.
Bye-bye.
See ya.
See ya.
Bye-bye.